All right, so first of all, thanks Tom for asking me to talk about this. I'm giving this talk on behalf of the LSE, but really many of the ideas for the connection with STROBE-X come from chatting with Tom. So I'm gonna start a little bit of the multi-messenger discussion here. And as you know, I think I don't need to say much about this. Luckily, we do have detections now, so I don't just need to give the usual talk about upper limits. That's the two LIGO detectors there. And as we know, we have been, well, the first observing run 01 is complete, and then since just August, the second observing run is also over. So far, there have been like 3 binary black hole events securely confirmed, 1 candidate, and this is part of the story we know. However, still, rather exciting for the fact that these binary black holes are more massive than we expected. I personally am looking forward to neutron stars, so I'll say a little bit more about these black holes and then try to shift to that topic. So the big challenge in terms of doing multi-messenger really astronomy with LIGO is the large error areas. As you can see here for the 3 events put together as well as the candidate there. And just to give you a sense of scale, so for the first event that was detected, the 90% confidence region was about 600 square degrees. So these are pretty large error areas, but it's not going to be always like this. We look forward to Virgo contributing to this localization. So what you're looking at here is how these localizations will shrink when you include simulated Virgo data, so going from there to there. And so particularly there's good prospects for shrinking this error areas. Virgo has been joining the later part of the second observing run, and I'll be saying a little bit about that. So regardless, in spite of these huge error areas, as you all know, there has been a massive effort to follow up the LIGO triggers in all sorts of wavelengths. So you see here a summary of the timeline and the various instruments that followed in the case of the very first event, 150914, going here from high energy all the way up to like radio. And this massive effort is continuing. Now for the binary black holes, I think the one interesting possible comparator that came out is from the Fermi GBM result regarding a possible gamma ray transient associated with that, which I'm showing here from the Fermi GBM team. Now it is an open question whether this is an exception or it could really be something we will be seeing with more binary black holes detections, but this is more or less where we stand for counterparts. And on the lower plot here, you're seeing a comparison between this gamma ray event that was found with other Schwarzschild GRBs plotted there in terms of energetics on the x-axis and peak energy on the y-axis. I'm sure there'll be more talking about this in the next talk. But so there's interesting possibilities with binary black holes, but we don't really expect much in terms of electromagnetic counterparts, or at least we hadn't for a long time. So the updates so far, and here I feel like more or less everyone knows what I can't say. So anyway, here's the official update I need to give. So August 17 official update is we have a very exciting observing run which has ended August 25. And there is the big deal of Virgo joining since August 1st, so towards the end of the run, although obviously not a comparable sensitivity with LIGO because it just switched on for the first time in advanced configuration. There are some promising candidates that have been identified in this run and have been sent to EM partners, so astronomical partners. And the analysis of these candidates is still going on, so in order to have a secure establishment of the confidence level, there needs to be some more time for the analysis. So that is the status of our end of the run, and so the key point is binary black holes are nice, but neutron star matter, at least my personal view. And so we're really looking forward at progenitor systems or gravitational wave discovery that have more mass around them so that we can expect some brighter electromagnetic transients. So here's the typical scheme that I'm sure you've seen many times. So the basic idea that you can have two major channels of gravitational waves, one which is the golden one, if you like, which is merger of compact binaries, neutron stars, or black hole neutron star systems, which are also thought to be associated to short GRBs. And then the massive core collapse, if in really extreme form, can also be emitting gravitational waves potentially detectable if you are optimistic. And this type of extreme core collapse is also associated with long GRBs. So thinking of the type of joint studies that could be done here between LIGO and STROBE-X, we first want to focus for a moment about short GRBs / binary neutron star systems. So this side of the plot here. And what is the status in terms of that? Well, from the expectations that LIGO has in terms of proceeding with increasing its sensitivity over the first observing run plotted there, 02 and 03, second and third observing run, what we can say is, based on the current estimates for binary neutron star rates, we're not surprised we didn't see any in 01, which is known result for now. And then in 02, as you can see, there are several possible scenarios that could lead you to say, okay, in principle, a detection is possible. It would not be shocking if there is no detection of a binary neutron star in 02. So that is the situation in terms of rate, but by 03 for sure, right, something must happen, or the rate estimates that we have so far are kind of wrong. So the progress is promising. Here's a summary of it. Here you're seeing LIGO, Virgo, and Kagra. And there is LIGO India not in here, but it is expected to come up sometime 2024 or after. But for now, we are around the 02 here. So here's Virgo joining range order of 25 megaparsec there. And for the O2 run, the sensitivity for LIGO was in between 60 and 100 megaparsecs. And these are ranges for binary neutron stars, expected ranges for binary neutron stars. So Virgo is expected to join fully over 03, and then when Kagra joins, there's going to be a network of free detectors, which is going to make a huge difference for what concerns localizations. There are two types of searches that usually LIGO has undertaken in conjunction with astronomical observations. So one is to use gamma ray triggers, so short GRBs, and go use those triggers and search for related gravitational wave signals in LIGO data. So that is what we call the external trigger search, because we use the gamma rays as our trigger. And this is the latest result that you see here. So LIGO, as we said during 01, hasn't observed any binary neutron star, but however has carried out a search for gravitational waves in coincidence with short GRBs. And you see here the cumulative distribution versus redshift. So these are population statements that LIGO can make based on upper limits. What you see here is the constraints from 01. The red line is what you expect based on short GRB observations. So you can see that the constraints still aren't quite reaching what we would expect for the short GRB population, but they should, if you extrapolate here the dashed lines, for the first 2 years of advanced LIGO and Virgo. So what this means is, with 2 years of full running of advanced LIGO and Virgo at nominal sensitivity, if we don't detect any binary neutron star, then there's something wrong with the connection between short GRBs and binary neutron star progenitors. Okay, so 2 years of nominal sensitivity should for sure get us there.
So the red line is known short GRB.
Right. Right, these are, the red line is the short GRB population. Right. And then these are, I think, order of, I believe there were 19 total in this plot for this O1 results. And so, oh, you mean in redshift?
Yeah.
Yeah.
Are there diagonal lines with a bin?
Yeah, I'm not sure about the binning here, but I'm fairly sure. No, this doesn't contain longs. Yeah, this does not contain longs. Yeah, I'm not sure about the binning, but there should be a 19 total. Yeah.
Well, I think that's all measured redshifts for short GRBs, but there were just 19 short GRBs that happened.
Oh, yeah.
I think that's what.
Okay.
Yeah. Oh, sorry about that. Yes, so these 19 GRBs are the ones that we can put constraints on and compare with, and that is the full population. Yes, okay. But with only 19, this is why this looks bad. So we don't have a good constraints on the rates there. So if you get more events, this is going to shift down, and then if you improve the sensitivity, it's going to shift to the right. So that's why then the extrapolations come here. Okay. So then, looking forward, then what are the localization areas going to be? As we said, we really want like at least 3 detectors. And then if you, in this lower panel here where you see the localization area are shrinking a lot, it's referring to the 2 LIGO Virgo and LIGO India. But we said before, probably Pagra is gonna reach the needed sensitivities first. But the message is that we're gonna shift from order 1,000 square degrees to 10 square degrees, and with 4 detectors, less than that. So the progress is towards having that massive electromagnetic follow-up be a lot easier than it is right now. In terms of follow-up not triggered by gamma rays, then this is a summary slide that I'm stealing from another LIGO presentation, and this is showing the possible X-ray counterpart. So if you get a gravitational wave trigger, and you might have missed the gamma rays because the jet of the short GRB is not aligned with you, then what could you expect to catch? So here is on-axis short GRBs in blue at a distance of 200 megaparsec, and then it's showing some off-axis GRB models. So this would be this sort of canonical short GRB afterglow. Off-axis model is you're far away from the axis of the jet, and some other more exotic models of isotropic X-ray emission, potentially powered by a magnetar surviving that binary merger. So these are the type of 0.2 to 10 kV fluxes that would be expected on those timescales. Now, I do need to point out that there's a lot of possible pattern in the parameters models that have been assumed to show these curves. So it's good to have an idea of what the zoo of possibilities could be, but you could easily shift these curves up and down based on the assumptions you make on several model parameters here. So there's room for both triggered observations with using gamma rays to tell LIGO where to look, and then the other way around, LIGO triggers, and there's X-ray follow-up to figure out exactly the nature of that trigger. Now the last type, the other type of gravitational wave triggers that could happen and are not quite the golden standard because we cannot really model gravitational wave waveforms accurately from these searches, so they're not as sensitive, is the realm of gravitational wave bursts. So anything usually referred to as lasting less than 1 second. And that could be depending on what type of flavor of core collapse you get, whether it's an ordinary, quote, supernova or an extreme core collapse like a long GRB which has a jet. Then the question is, what is the rates of these events? And here I'm quoting the observed rate of long gamma ray bursts there, which is a factor of 10 less than what inferred for short GRBs, so it doesn't look very promising. On the other hand, we do know that there's a population likely of low luminosity long GRBs, which are the 980425 like, And those are inferred to have higher rates, so maybe there is some more positive prospect there. Again, here you need to think about that the only models likely that you're going to constrain are the more optimistic ones. So you need to have at least 10 to the minus 2 solar masses of energy going into gravitational waves. In any case, even for long GRBs, LIGO has been pursuing these searches, and here's a similar plot. So these are the constraints got in 01. I believe these were roughly 30 long GRBs. That is the observed distribution again, and this is how that you would push those constraints with 2 years of advanced LIGO inverter running. The blue and the red lines have the same amount of energy in gravitational waves, but the blue model here is spreading it over a duration of 100 times longer, so that's why the constraints are a little worse. So the message to take home out of here is, if we have 2 years of full run, then LIGO will be able to exclude some models, but only the most optimistic ones for the core collapse case. Now, this isn't the only, these two families that I've described, binary neutron stars, or if you like, in spirals and bursts, aren't the only thing going on. So there is a lot of in-between type of analysis which LIGO is developing. And here is usually what we were used to think of when we think of gravitational wave data analysis. There's the short duration signals, the long ones. So here is, for example, persistent sources like neutron stars and pulsars. And then there's the binary neutron star up here, which falls in the well-modeled category. The bursts, like the core collapse, which are short and badly modeled. But what LIGO is doing right now is we're also working to try joining this different, I won't talk about very much about the stochastic one, but we're trying to join these different categories of analysis. So for example, what if you had not so well modeled signal, but of longer duration than a burst, so you would start joining these two different rheums there. So in this sense, the work that LIGO is doing could help to answering some open questions that we still have about gamma ray burst central engines. And one key question is, what happens after the two neutron stars merge or the core collapses? Is there a black hole being formed right away, or is there a post-merger or post-explosion remnant which survives longer? And this has been motivated by the observations of what we call X-ray plateaus in the afterglow of both short and long GRBs. So this is time-series trigger, and we would expect an X-ray afterglow light curve going down as a power law, so a line here in log scale. But sometimes, often in long GRBs for sure, we see this plateau case. So the question is there a neutron star surviving there with high magnetic field pumping energy? And so can we probe it using gravitational waves? There are efforts going on to do that. And so the question is whether STROBE-X could help with figuring out exactly what is the nature of the post-merger or post-explosion remnant, depending on whether you're considering a long or short GRB. So I'm stealing these plots from Rawlinson et al. 2013, which are showing the typical plateau duration here in seconds. So here it starts at 100. And then the plateau flux in 0.3 to 10 kb. That is 10 to the minus 12, 11, minus 10. And so this is showing a sample of short GRBs for which that plateau feature has been seen. And the point is, so can we first of all probe these fluxes, and then the other open question would be if there is really a neutron star or magnetar pumping energy in there, while LIGO might search for gravitational wave signals, can something like STROBE-X go and hunt for potential pulsations in that plateau phase? And I will just mention one last thing, which is another open question that STROBE-X might probe, which is the nature of X-ray flashers. So softer GRBs. So X-ray flashers resemble GRBs in almost every respect, but the flux comes mostly from X-rays. Beppo-Sachs and Hedy-Hugh have done a lot to unveil this population, but then the progress has a little bit stalled after that. because we would need, again, softer measurements in the X-rays. So here's a plot which is comparing standard GRBs in green, the Baxi sample, and in red you're seeing the 82 sample, that's fluence in 1500 kV, and then the peak of the observed emission. So these are softer events. And the really interesting thing for LIGO would be in terms of rates, because the rates is constrained to be basically in between that of the short GRBs and the really long soft GRBs. So it's supposed to be 10 times that of classical GRBs, so it would be more promising than the standard cosmological GRB, although not as promising as the low luminosity long GRBs that I mentioned before, which would be could be even higher rates. So that's a question not just about finding them, first of all, potentially pushing joint studies with LIGO, but there's also an understanding missing right now, which is why are they softer? Are they maybe observed boxes coming from structure, jets, and so on? And I will just leave it there and leave you my summary.